Hello everyone, welcome to my channel Chem Insider. So in today's class we will be discussing about hybridization of orbitals involving the d orbitals also. So in the earlier videos we learned about the hybridization of certain compounds or molecules where there is just involvement of s and p orbital. When you come across the elements present in the 3D series, that is the elements present in period 3, if we consider for the elements present in period 3, they have their valence shell with 3s, 3p and 3d. That means they will be having an empty d orbital present in it. So for the elements which are present in the period of n is equal to 3, they have an empty d orbital along with 3s and 3p orbitals. So therefore these particular elements which have a d orbital present in them, they might also involve those particular d orbitals for the respective hybridization. And similarly when compared to the hybridization involved in compounds of period n is equal to 2. And further, what we have observed in the previous classes is that this 3d orbital comes after the 4s orbital of the periodic table. That is 3s, 3p comes before 4s and later comes the 3d orbital. Therefore, what we observe is this energy of this 3d orbital, the energy of this particular 3d orbital is almost equal to the energy of the 3p, 3s, energy of 3p, 3s. Therefore, it may undergo hybridization from 3s, 3p, 3d. And further, the energy of this 3d orbital is quite similar, almost similar to 4s and 4p orbital also. Therefore, it might also undergo hybridization involving 3d, 4s and 4p orbitals. Therefore, the d orbitals present in any element may undergo two types of hybridization, where it may be of sp3 type, spd type, or it might be dsp type of hybridization. And further we need to remember one point is 3p orbital will not have energy similar to 4s. 3p orbitals will not have energy similar to 4s, and therefore there will be no hybridization involving 3p, 3d and 4s orbitals. Okay, so this particular hybridization is not possible. That is because hybridization is only possible under the condition if the orbitals are of almost same energy. Since 3d orbital has almost same energy when compared to 3s, 3p and also when compared to 4s, 4p, they undergo two types of hybridization, in which it may undergo the hybridization in the same valence shell, or it may be because of the two different valence shells. Okay, but if you consider for the 3p orbital, it will never undergo hybridization with the orbitals of 4s. That is because energy of 3p will never be same as of the energy of 4s. So we come across certain different type of hybridization of d orbitals along with s and p, which results in certain different geometries. Okay, so we have 4 or 5 types of hybridization which involves d orbitals, and their respective geometry and structures. We'll discuss that now. So now we'll be discussing about hybridization involving d orbitals. Hybridization involving d orbitals. So as I said, d orbitals, for example of 3d elements, they might be undergoing hybridization along with the 3s, 3p orbital, or it may be undergoing hybridization with 4s, 4p orbitals also. So now let us consider certain hybridization types. So there are 4 types of hybridization. One in which we have Sp2 D hybridization. Sp2 D hybridization. It forms 4 Sp2 D hybrid orbital. That gives us a tetrahedral geometry. They give us tetrahedral geometry of the type Sp2D. Example, nickel tetrachloro groups, NiCl4 compounds. They undergo Sp2D hybridization to form tetrahedral geometry. Then we have one more type of hybridization with the same, that is 3d orbital 4s and 2 of the 4p, that is Dsp2 hybridization, where they form square planar geometry. If a molecule undergoes Dsp2 hybridization, then it will be forming a square planar geometry. Example, nickel tetracarbonyl, NiCO4. Not this Cl, this will be Cl. Okay, so if you consider for the Dsp2 hybridization, then if a molecule undergoes Dsp2 hybridization, then it will be forming a square planar geometry. Example is nickel tetracarbonyl, where nickel is undergoing Dsp2 hybridization. In the same case, nickel may also undergo Sp2 D hybridization to form nickel tetracyanate in a tetrahedral geometry. Next, we have one more type of geometry where hybridization is Sp3 along with one of the D orbital. If we observe Sp3 along with one of the D orbital, they form trigonal bipyramidal geometry. They form trigonal bipyramidal geometry. Trigonal bipyramidal geometry. For example, Pcl5, phosphorus pentachloride, undergoes Sp3D hybridization to form trigonal bipyramidal geometry. There is one more type of hybridization. This is because of 3s, 3p and 3d. If there is hybridization involving 3d, one of the 3d orbital, one of the 4s orbital and 3 of the 4p orbital, then it forms Dsp3, it forms square pyramidal. It forms square pyramidal. It undergoes Dsp3 hybridization to form square pyramidal geometry. Example, we can consider Br(F5). Example for square pyramidal geometry is bromine tetrapentafluoride. Okay, so this is an example for Dsp3 hybridization. Next, if compounds undergo Sp3 D2 or D2 Sp3, if your element present in a molecule undergoes Sp3 D2 or D2 Sp3 hybridization, they are often found to form a same geometry, that is octahedral geometry. They form octahedral geometry. Example, sulfur hexafluoride. So these are the different type of hybridization which involves d orbital in them. It might be 1d orbital or it may be 2d orbital, as we have observed over here. And there is one more type of hybridization where we observe that Sp2 D2 hybridization. That is Sp2 D2 hybridization. They almost similarly give away the square pyramidal type of geometry. Okay, so this is about the different types of hybridization involving d orbital. So now let us discuss about the hybridization possible and the structure of Pcl5 and Sf6 molecule, which is there in your syllabus. Now, for first one, structure of Pcl5 and its hybridization. Okay, so the phosphor in Pcl5 is of atomic number 15. The atomic number of phosphor in Pcl5 is 15. So if you write down the electronic configuration, it has 1s2, 2s2, 2p6, 3s2 and 3p3 along with 3d0. Okay, so it has 1s2, 2s2, 2p6, 3s2, 3p3, 3d0. If you write down the ground state electronic configurations orbital, so that will be 2 electrons in 3s orbital, 3 electrons each in 3p orbital and 0 electrons in the 3d orbital. So now what happens over here is, in the excited state, one of the 3s electron jumps to the empty d orbital. One of the 3s electron jumps to the empty d orbital, leading to the formation of 1 electron in 3s, 1 electron each in the 3p orbitals and 1 electron in the one of the empty d orbital. So therefore it undergoes Sp3D hybridization. Sp2 D hybridization to form 5 Sp2 D hybrid orbitals. It forms 5 Sp2 D hybrid orbitals, and these hybrid orbitals of phosphor align themselves in such a way that 3 of the Sp2 D hybrid orbital, 3 of the 5 Sp2 hybrid orbital. So we have total 5 Sp2 D hybrid orbitals, out of which 3 of them will be in equivalent position, that is equatorial position. 3 of them will be in equatorial position and 2 of them will be in axial position. Okay, 2 of the 5 Sp2 D hybrid orbitals will be in the axial position and the 3 of them will be in the equatorial position. So therefore, if I write equatorial position orbitals in yellow chalk paste, so those are like this, which is one is in this direction, one is in this direction, and one is in this direction, and those which are in the axial position will be in this direction. So if you consider for the geometry, let us say if this is the plane of Pcl5, this is the plane, phosphorus will be present at the center, similar to the boron trichloride structure, Bcl3 structure. So we have, if you consider for the Bcl3 structure, if you consider this as the boron, we had one chlorine here, one in the away from the observer, one towards the observer, right? Similarly, Pcl5's 3 of the Sp2 hybrid orbital, if you consider P at the center, one will be in the plane, one will be towards you, and one will be away from you. All of this in the same equatorial position. Okay, that is the horizontal plane. Next, 2 of the Sp2 hybrid orbital will be in this particular axis, z-axis. Okay, one at the top, one at the below, such as I have written over here. So these 3 hybrid orbitals will be in one plane, and these 2 hybrid orbitals will be in axial axis. So if you consider this as the z-axis, so this will be in this 3 particular direction. Okay, so such is how we observe the Sp2 D hybridization, where we get trigonal, that is a triangle on both sides. If we join these 3 at the triangle's 3 sides, it forms a pyramid. Therefore, this particular geometry of Pcl5 is called trigonal bipyramidal. Trigonal bipyramidal, that is, it forms pyramid on both sides. It forms pyramid on both sides of the equatorial 3 Sp2 D hybrid orbitals. So it forms 5 Sp2 D hybrid orbital, out of which 3 of them will be present in a plane with the bond angle of these 3 similar to 120 degree. So P has 3 of those Sp2 D hybrid orbital at 120 degree to one another. So the bond angle of these 3 will be 120 degree to one another, and the 2 orbitals which are present in the axial position have their inter bond angle of 180 degree, and the bond angle with these 2 will be 90 degree. Okay, bond angle with one of the axial bond and the equatorial bond will be 90 degree. Bond angle of 2 equatorial bonds is 120 degree. Bond angle of 2 axial bonds is 180 degree. So the 5 chlorine atoms, that is of the Pcl5's 5 chlorine atom, will donate 1 electron each to the hybrid orbital to form pairing, such as like this. Okay, each of the chlorine have 1 electron in them. In their valence shell, there are 7 electrons. It requires 1 electron. Therefore, they share the electrons of this 5 Sp2 D hybrid orbital, donating 5 electron to them. Therefore, it forms the 5 positions of this trigonal bipyramidal structure. So this is how Pcl5 is formed. Further, what we observe is, if you consider for the bond strength of P in the axial positions and the equatorial position, the bond of P and Cl, bond P and Cl bond at the axial position is slightly weaker when compared to the equatorial PCl bond. Okay, axial PCl bond is slightly weaker when compared to equatorial PCl bonds. So that is one point you have to remember for a long time. So axial PCl bond is weaker when compared to equatorial PCl bond. Okay, so this is about the structure of Pcl5. Next, we'll discuss about the structure of Sf6. So, sulfur hexafluoride compound. Sf6. So, sulfur hexafluoride compound has sulfur with atomic number 16. So, if we write the ground state electronic configuration for this, it will be 1s2, 2s2, 2p6, 3s2, 3p4, 3d0, 3s2, 3p4, 3d0, and now in the excited state it forms an orbital of one of the electron of s orbital and one of the paired electron from the p orbital jumps to the empty 2 d orbitals. So if you consider the p orbital and d orbitals, so this is the 3s, 3p and 3d. Each of them had like this electrons present in them, 3s2, 3p4 and 3d0. What happens in the excited state is one of the electron from 3s orbital and one of the electron from 3p orbital jumps to the empty 3d orbitals. So therefore it undergoes Sp2 D2 hybridization, where that is 1 3s orbital, 3 3p orbitals and 2 3d orbitals, leading to the formation of Sp2 D2 hybridization, where it forms 6 Sp2 D2 hybrid orbitals. It forms 6 Sp2 D2 hybrid orbitals. These 6 Sp2 D2 hybrid orbitals are arranged themselves in the space in an octahedral geometry. If you consider this as a sulfur, so 4 of the 6 Sp2 D2 hybrid orbital will be in one plane. So that is, if you consider this as the plane, so 4 of the orbitals will be in this direction, 1, 2, 3 and 4, and 2 of them will be present towards you and away from you. Okay, 4 of the orbitals will be present in one plane and 2 of the 6 Sp2 D2 hybrid orbitals will be present towards you and away from you. Now if you consider for the geometry like this, sulfur with one orbital over here, 1, 2 over here, 3 and 4, fifth one will be above, sixth one will be at the bottom. So now if you write down the bonds joined over like this, okay, so these 4 in one plane, okay, so these 4 are in one plane, whereas the fifth and the sixth are placed above and below the plane. Okay, out of the 6 Sp2 D2 hybrid orbital, 4 Sp2 D2 hybrid orbitals are present in one plane, and 2 of them will be present above and below the plane, equidistant as when compared to the equatorial positions also. Okay, when you come across this particular geometry of octahedral Sf6, the bond length of equatorial Sf compound and axial Sf bonds, which is formed when 6 fluorine atom donate 1 electron each to the 6 Sp2 D2 hybrid orbital. We have 6 fluorine atoms, each of them will be donating 1 electron to the 6 Sp2 D2 hybrid orbital, therefore obtaining the positions of the octahedral corners. So each of the fluorine atom will be present like this at the octahedral terminal positions. Okay, so each of these fluorine atom bonds will be equal to one another, that is sulfur fluorine bond in the axial position will be equal to the sulfur fluorine bond in the equatorial position. That is because each of these bonds will be away from one another at an angle of 90 degree. The bond angle between these two bonds is 90 degree. Bond angle between these and these bonds are again 90 degree. Since all these 6 Sf bonds are away from one another with a bond angle of 90 degree, all these 6 bonds will be similar in energy and will be having same length. Whereas if you consider for the Pcl5 molecule, axial PCl bonds were of higher bond length, equatorial PCl bonds were lower wavelength, lower bond length. Therefore, we observed that strength of equatorial PCl bonds are high, whereas compared to the strength of axial PCl bonds. In case of Sf6 molecule, all these 6 Sf bonds are equal in length and have a same strength. Okay, so this is how the Sf6 molecule is formed by undergoing Sp2 D2 hybrid orbitals, where out of the 6 Sp2 D2 hybrid orbital, 4 of them will be in plane and 2 of them present above and below the plane. Since all of them are of the same length, we can clearly alter the positions of the fluorine atoms also, and they does not affect any of the orbitals geometry or property. Okay, so this is about the hybridization of molecules or compounds involving d orbitals in them. In the next class, we will be discussing about the molecular orbital theory. I hope you have understood the concepts which I explained. If you have, please do subscribe to my channel and share this video among your friends. And thank you for watching.